All right. All right. Hello everyone, and it's nice to see you all. And we had quite quite a summer break, if we can call it this way. Um, Quite a summer we had. But now we're back again, and we are absolutely pleased to have a really fascinating lecture today by our visiting guest. So, without further ado, I'll just introduce our speaker for today. Floris Cohen studied history in the late 1960s. He is a professor emeritus in the comparative history of science at Utrecht University in Netherlands. His first book in English was Quantifying Music, the Science of Music at the First Stage of the Scientific Revolution, 1580 to 1650. He is currently completing How Our World Has Become Modern, a threefold revolution. In or about 1968, a fellow student took him to a harpsichord concert given in a cold, half-filled church in Haarlem by a certain Gustav Leonhard. That is how he learned of the early music movement, with Leonhard together with Nicolas Harnoncourt as its great pioneer. The movement has kept his faithful allegiance ever since. In 1971, he began to learn to play the church organ on one of Holland's finest and largest Baroque organs. He became in due time an advanced amateur capable of playing pieces like François Couperin's Messe des Pranceurs, Paroisseurs. After a year-long everyday practice for at least 1 hour, Bach's Toccata and Fugue in G. So without further ado, we start by listening to an excerpt, and then Floris will start his lecture. So I will just share my screen and we will start.
Dear audience, suppose that you and I had been living 4 centuries earlier. Suppose that in the year 1625 we have been invited to attend a performance of the piece you have just heard, Allein Gott in der Höhe sei er, by Michael Pretorius, the composer and music theoretician who designed the organ that you have just heard being played by Jean-Charles Ablitzer, and that was built in 1610 by Esaias Comenius. Back in 1625, our individual aesthetic and emotional sense would have been struck by the music in about the same way it has struck you and me now. However, back in 1625, we would, at a perhaps less conscious yet an assuredly present level, have experienced the music and its performance as something else in addition. The technical term for that something else is musica instrumentalis. In spite of what it looks like, that Latin expression cannot be translated as instrumental music, even though it is true that that is what it came to encompass as well. But the expression encapsulates more than that. Indeed, the performance you have just attended, which was with instruments and song, falls straightforwardly under this category of musica instrumentalis. A more correct translation of the expression would therefore be music as actually composed and performed. And it is in that sense that musica instrumentalis served as the counterpart to two other closely related categories, musica humana and musica mundana. The latter category should likewise be by no means translated as what it superficially looks like, that is, as worldly music. No, the correct translation is cosmic harmony. This, indeed, is the key concept of my entire talk, which is chiefly about the early stages of its definitive unraveling. Okay, what about this conception of cosmic harmony? It was, quite literally, a world-encompassing conception, which goes back to many thinkers, but to two in particular. The one was a Roman senator in the early 6th century by the name of Boethius, the other a probably no more than legendary figure of more than a millennium earlier, who lived on the Greek island Samos by the name of Pythagoras. We start with Pythagoras. Tradition attributes to him a remarkable discovery. As we all know, when you produce two arbitrarily selected musical sounds at the same time, the combination does not sound at all well. The result is most likely to prove quite jarring. The resulting interval sounds decidedly unpleasant. Not in all cases, however. There are certain exceptions, where the sounding together produces a satisfying sense of mutual fit. To a certain extent, the two notes seem to blend. We still use the Latin terms for the two cases, the customary and the exceptional one. We call the customarily jarring intervals dissonant, the exceptionally blending ones consonant. Now take note of the following. If you cause a string to vibrate, thus producing a musical note, and then halve the string and produce another note, you find that the two notes blend quite well. We all know that consonance. We call it the octave. If you similarly take a string and the same or another one at 2/3 its length, you get a somewhat less thoroughly blending, but still quite consonant interval, the fifth. Likewise with the fourth, which you produce by sounding a string and then one at 3/4 of its length. So we have now found that the octave can be represented by the simple integral ratio of 1:2, the fifth by 2:3, and the fourth by 3:4, thus demarcating the consonant intervals from all remaining intervals, the dissonant ones. But the principal message is far more general. Pythagoras had found an intimate connection between two seemingly wholly disparate phenomena, between sound and number, or rather, between pleasing sound and number. How could that be? We modern people would say at once that what brings out the connection is the phenomenon of setting a string in motion in the first place. That's to say, We look for an explanation in how the strings, so as to produce their sound, are vibrating, such as to appear to display the simple regularity that Pythagoras is reputed to have discovered. Here, however, is Pythagoras' own explanation. And even though he ignored the very vibrations that produce the phenomenon, his explanation is of truly staggering boldness. The close connection between pleasing sound and the numerical regularity that appears to underlie it, so he maintains, can only be there because the entire world we live in is, in the final analysis, governed by number. Phrased somewhat differently, the universe is a case of a harmony that can be expressed in numbers, or, more precisely, in the simple ratios of the first few integral numbers, that is, in the range of integral numbers 1 to 4. Signs of this harmony can be detected in many directions, at many places, and in many senses, notably in a certain harmony thought to obtain in the heavens. Even though it is true that we cannot hear it, we can only recognize it by means of the intellect. I now jump a millennium ahead and land in Rome in the office of the senator, philosopher, and mathematical theorist Anicius Manlius Severinus Boethius. We encounter the account of cosmic harmony that he adopted from Pythagoras and then developed in several directions in his treatise De Institutione Musica, The Principles of Music, which he wrote about 510 AD. The conception of cosmic harmony unfolded therein was to remain of substantial significance in all Western thought, both inside and outside the world of music, strictly speaking, until far into the 17th century. By way of illustration, I quote the first stanza of John Dryden's Song for St. Cecilia's Day, written in 1687. From harmony, from heavenly harmony, this universal frame began. When nature underneath a heap of jarring atoms lay and could not heave her head, the tuneful voice was heard from high, arise ye more than dead. Then cold and hot and moist and dry, in order to their stations leap, and music's power obey. From harmony, from heavenly harmony, this universal frame began. From harmony to harmony, through all the compass of the notes it ran, the diapason closing full in man. To return now to Boethius' conception, consonant intervals are represented by ratios of integral numbers as the octave by 1 to 2, the fifth by 2 to 3, the fourth by 3 to 4. These ratios are nothing less than the fundamental constituents of the world. According to this model, there is a cosmic harmony, not really audible, but still universally present, in that we can grasp its presence by means of our intellect. It takes three closely connected forms. There is musica mundana, cosmic harmony in the widest sense of the music of the spheres, that is, of harmonic relations not as such audible, yet held to mark many a heavenly phenomenon. There is musica humana, the manner in which cosmic harmony stands reflected in each of us individually, in our bodies no less than in our souls. Recall here Dryden's line, the diapason closing full in man. And there is, finally, musica instrumentalis, the audible music that, whether it be sung or played on a musical instrument, we actually make and listen to. Which means that our bodies, our souls, and our music all partake of cosmic harmony. They exemplify it, though imperfectly so. We are, after all, fallible humans. Consequently, whatever piece of art music we find ourselves playing or listening to, we are not just enjoying a well-written and well-executed piece, but we also partake in what binds the cosmos together. A bond that stands expressed in its turn in the numerical ratios that constitute the tuning of the world. You'll see now three pictures, all taken from a 1617 book by Robert Flood, a physician with chiefly occult interests, in which this conception is symbolized in a very much personally colored but also gripping manner. This harmonic worldview, marked by a striking intricacy and even beauty, had been built with as its center the consonance producing capacities of the four numbers 1, 2, 3, and 4. Cosmic harmony was a grandiose way to make sense of what holds the created world together, by binding macrocosm and microcosm, the heavens and human beings, tightly together by means of a fixed rule of numbers. Numbers not selected at will, but found to stand expressed in our intimate musical experience. Cosmic harmony was a beautiful conception. It was a reassuring conception. It was also, in retrospect, a risky conception. Grandiose views of the world at large, such as in the Western world proliferated in ancient Athens and spread all over Europe a millennium and a half later, cannot be proven. But as a rule, they cannot be refuted either. When, in exceptional contrast, you build a worldview around numbers and certain numerical relationships, you may deservedly feel satisfied to have built on more solid ground for as long as the numbers fit well. But no sooner does the fit appear to be less than watertight, or the very ground on which the conception has been built is bound to turn dangerously shaky. Let me repeat this sentence, as it provides the key to all that follows. When you build a worldview around numbers and certain numerical relationships, you may deservedly feel satisfied to have built on solid ground for as long as the numbers fit well. But no sooner does the fit appear to be less than watertight, or the very ground on which the conception was built is bound to turn dangerously shaky. In what ways, then, could the fit produced on the basis of the four consonants building numbers 1, 2, 3, and 4 appear to be less than watertight? We may distinguish between two principal ways. You might argue that the numbers were not the right ones, or you might argue that numbers are not suitable entities to provide, let alone undergird, a conception of what holds our world together. Both arguments have made their historical appearance, each with varieties of its own, and from here on my lecture is dedicated to presenting them to you. I discuss these varieties in chronological order. The first event that came to upset cosmic harmony was the introduction, early in the 14th century, of the major and minor thirds and sixth in chord harmony. When we listen to polyphonic music composed earlier, in, say, the early Notre Dame school, we readily notice the complete absence of chords central to centuries of later music making, the triad. And the triad was absent for a very good reason. In a Pythagorean tuning, both the major and the minor third are hopelessly off tune. They are just harsh dissonances. Some simple arithmetic can show you why. With the size of the fifth, 2 to 3, and of the fourth, 3 to 4, given, the size of their difference, which is of course the whole tone, becomes 2 to 3 divided by 3 to 4, which equals 8 to 9. Now add two whole tones, which in musical arithmetic is done by multiplying them, and you get 64 to 81 for the major third. But since the consonances are given by ratios of the first few integral numbers, we can already deduce from sheer arithmetic that this major third will be a very harsh dissonance, as indeed it is. This particular variety of the major third is called the Pythagorean third, and we can readily understand why in everyday musical practice it had to be shunned at all costs. Until the third was no longer shunned. Early on in the 14th century, with the composer John Dunstable leading the flock that followed, the major and minor third did make their appearance in the art music of the time. But how could that be? That became a big problem for music theorists who, however much given to tradition hallowed thinking in terms of cosmic harmony and all that it entailed, could not keep ignoring what went on in everyday music making. they began to realize that musicians were using another major third, one not defined by the ratio of 64 to 81, but by 4 to 5. Similarly so with the minor third, 5 to 6. Similarly so with the major sixth, 3 to 5. Similarly so with the minor sixth, 5 to 8. But how could these four consonant intervals be fitted into the standing account of the harmony of the world? The ingenious answer that quickly became predominant over the second half of the 16th century was given by Gioseffo Zarlino, not only Maestro da Cappella at St. Marco Cathedral in Venice, but also a very learned person skilled in musical theory as well as in all-round Greek philosophy. His solution to the problem comes down to a drastic revision of the harmonic number. In the Pythagorean tradition, the harmonic number, the number that demarcates the consonants producing ratios from those that involve dissonances, had been given by the so-called tetractys, the range of numbers 1, 2, 3, and 4. In his treatise Le Istituzioni Armoniche of 1558, Zarlino replaced the tetractys with the scenario, the range of integer numbers from 1 through 6. These numbers, so he argued, suffice to produce all consonant intervals, the thirds and sixths now also included. Out of their bounds lies the vast domain of the dissonances. But what then is so special about the scenario that enables it now to form the, as it were, restored rock bottom of nothing less than the harmony of the world? At this critical point, Zarlino came forward with a whole range of considerations, such as the fact that 6 is the first perfect number, meaning that it is the first of those numbers that are themselves the sum of all factors into which they can be resolved. In the present case, 1 times 2 times 3 equals 1 plus 2 plus 3. Furthermore, God needed 6 days for the creation. There are 6 planets. There are 6 directions. A cube is delimited by 6 surfaces, and so on and so forth. As you have been taking in Zarlino's explanation of what makes the number 6 so special as to enable it to constitute the scenario and thus, in a sense, to hold the whole world together, it may well be that one little anomaly has come to stick in your throat. What about the ratio of the minor sixth, 5 to 8? How can Zarlino possibly have overlooked this unfortunate circumstance? Well, of course he didn't overlook it, only he couldn't use it. So he explained the 8 for the minor sixth away as please to be regarded in this special case as twice 4. Why, so you may want to know next, why had Zarlino not made things a good deal easier for himself? Why not proclaim not the scenario, but the ottonario, that is, the range of integral numbers 1 through 8, the true harmonic number out of which all consonances are flowing? Well, you can guess. In between 6 and 8 stands 7, a number that does not produce any readily known consonant interval. So the scenario it had to be, and Zarlino stuck to it. The theoretical challenge brought about by those thirds and sixths that were so enjoyably at work in musical practice had been withstood. Cosmic harmony had been rescued. Not that the apparent success of Zarlino's heroic saving operation was to last long. It is not only you, my modern audience, that has smelt something fishy about various considerations of his, most obviously those with the minor sixth, but more generally as well. Doesn't all this come down to sheer number juggling? Is what I believe I have caught several among you thinking. Nor are you the first to think so. Already one generation after Zarlino, basically the same thought occurred to some of the brightest men of the period. Please recall at this point that the thoroughgoing critique of cosmic harmony could go in 2 distinct directions. One of these are the wrong numbers, and the one of numbers are just not the right entities. We have seen how, by replacing the Pythagorean tetractys with the scenario, Zarlino sought to overcome the first of these two considerations when it manifested itself for the first time. We shall now take up at bottom the same argument, these are not the right numbers, in its second appearance. Our protagonist is a Dutch scholar-engineer, Simon Stevin. In a collection of essays that came out in 1608, and that was meant to cover all the mathematical sciences of the day, a treatise on musical theory could hardly be missing. So he wrote one and entitled it Van de Spiegeling der Zinkunst, on the theory of music. At the heart of the treatise is Stevin's conviction, for which he adduces several very interesting and very smart, yet profoundly mistaken arguments that the scenario, that is, the numbers 1 through 6, neither does nor can stand for the mathematical counterpart to the musical phenomenon of consonance. His key point is that Zarlino has failed to capture what is so fundamentally wrong-headed with this meanwhile ingrained habit of deriving the consonant intervals from what mathematicians are used to calling harmonic proportionality. The right kind of proportionality, Stevin argues, is rather so-called geometric proportionality. Consequently, the notes inside the octave that we regularly make music with, from C to higher C, are given by the 12th root of successive powers of 1 to 2. With only the octave remaining unchanged, that is, as 1 to 2, the 5th becomes the 12th root of the 7th power to 1 to 2, the major third, the 12th root of the 4th power to 1 to 2, and so on. It may be that you recognize Stevin's proposed division of the octave, since it is mathematically equivalent with what by the early 19th century became and has since remained the predominant tuning system, so-called equal temperament. Conceptually, however, Stevin's division and equal temperament could hardly be more different. And it is not for nothing that the few people who had a chance to read his treatise, it was not published until late in the 19th century, found his proposal simply mistaken, not to say ridiculous, at a very deep level. Stevin probably failed to publish it himself in view of a scathing critique he received from an organist of his acquaintance. Given that almost none of his contemporaries had a chance to read it, or even to learn about it, it may look as if it remained without any consequence for the post-Zarlino fate of cosmic harmony. In a sense, that is of course true, but in another sense not. One very remarkable thing about this mathematician's treatise on musical theory is that its dual subject is consonance and the division of the octave, but that he treats these topics in the absence of any framework of cosmic harmony. For him, Pythagoras is just an early mathematician with the wrong-headed idea of true proportionality. In no way the man who began to interconnect by means of numbers and their ratios the universe and us human beings and the music we make in a so deeply meaningful a way. Among the very rare readers of Stevin's treatise was a Dutch candle maker and graduate theologian by the name of Isaac Beekman, who had a chance to borrow it from Stevin's widow. No portrait of Beekman exists, so you must make do with his signature. From 1612 onward, he kept a scholarly diary, but he never managed to organize its contents into a publishable treatise, which is most probably why you have never heard of him. This in spite of the circumstance that eventual publication of the diary by mid-20th century has gradually paved the way for recognition of both the profound originality of his thought and the considerable impact it indirectly exerted on, notably, two French friends of his, the philosopher René Descartes and the extensive writer on music from an empiricist point of view, Marin Mersenne. For Beekman, no less than for Stevin, but in a very different manner, Zarlino's numbers form quite the wrong approach to, yes, to what? Well, not to cosmic harmony, as Beekman in the quite numerous and at times lengthy notes about musical theory in his diary remains as silent about anything that even smacks of some universe and man-encompassing harmony, as we have just found to be the case with Stevin's treatise. For Beekman, musical sound is a special case of sound as such. and in his view, sound is particles. Not that there is anything special about that, as in Beeckman's atomism-inspired view, the entire world is particles, or rather, particles in incessant motion. And it is these incessant yet rule-obeying particle motions that hold his abiding interest, in the case of sound as well as of just about anything else in the world. Beeckman followed the ancient atomists in taking sound to be made up of a succession of invisibly small particles emitted by the sounding body. On how this comes to pass, he was a good deal more specific than they had been. He assumed that the vibrating string cuts the ambient air into tiny globules that are set in motion by the force of the vibrating string. As for pipes, be they wind instruments or human throats, sharp edges near the hull where wind enters cut the wind into globules, and the resulting increase in inside air pressure ejects them. He further associated loudness with the amount of globules, or alternatively with the density of their aggregate. Pitch he attributed to their speeds, or alternatively to their sizes. A string twice as short as an otherwise equal one cuts off globules twice as rapidly and or twice as many small ones. Consonance comes about in the following manner. In moving to and fro, the string at midway cuts off its maximum number of globules. At the points of return from to fro and vice versa, which provide moments of intermediate rest, no globules are cut off at all. Hence, at each given length of the string, each note is marked not only by a definite pitch, but also by a sound silence pattern of its own. In musical intervals, then, the more often such momentary sounds coincide with sounds and momentary silences with silences, as they do all the time in unison, every second time in the octave, and so on, the more consonant the interval is. From this follows a table of degrees of consonance. For example, the fifth, 2 to 3, is more consonant than the major third, 4 to 5. The explanatory schema just sketched was hardly without problems of its own, and Beeckman courageously went on to meet them. I mentioned just one such problem. It concerns the same number 7 that had caused Zarlino such headaches, in that it made it impossible for him to settle on the ottonario, the range of integral numbers 1 to 8, that would have spared him explaining the ratio of the minor 6, 5 to 8 away. For in Beeckman's table of descending degrees of consonance, which of course starts with the octave 1 to 2 and ends with the minor 6, 5 to 8, the ratio of 4 to 7, which stands for a non-existent interval, even precedes the ratio of the minor third, which after all is 5 to 6. But I must leave it at that, though not without noting that the two-man Beeckman influenced so profoundly on the subject, Descartes and Mersenne, did seek in their turn to come to terms with both this and a range of similar problems. Mersenne doing so in 1637 in a work with the title still vividly reminiscent of cosmic harmony, his Harmonie universelle. Meanwhile, Beeckman was not the only one who, at least a decade ahead of both Descartes and Mersenne, found himself dealing in the late 1610s, early 1620s with issues of consonance and the division of the octave, in a context meanwhile far removed from cosmic harmony. In Tuscany, another, still far deeper thinker about the structure of the physical world sought to come to grips with musical phenomena, to which the issue of consonance was key. This was Galileo Galilei. He did not publish the outcome until the masterpiece of his late age saw the light of day, the Discorsi of 1638. But there are indications that the solution he was to publish then and there had already occurred to him in the 1610s. In a manner radically different from Beeckman, Galileo also put a long-standing account of consonance due to ratios of the first few integers upon a new physical foundation. He recognized that pitch is uniquely determined by the frequency with which a vibrating string moves to and fro. Quite unlike Beeckman, with his imaginary sound globules being cut off by the vibrating string, Galileo adopted the pulse account of sound production. Here, musical sound is yielded by the successive pulses transmitted from the vibrating string through the air to our sense of hearing. This implies that if two different notes are made heard simultaneously, pulses coincide in those cases when the intervals in question happen to be given by ratios of the first few integral numbers. In the case of the octave, 2 to 1, every second pulse yields such a coincidence. With the fifth, 3 to 2, every sixth one, and so on, up to and including the minor sixth, 8 to 5. Which means that Galileo arrived at the same table of descending degrees of consonance as, in another manner, Beekman did. Only, the traditional range of consonant-yielding ratios is now linked solidly to the physical parameter of vibrational frequency. Does this mean that the solid criterion demarcating consonant from dissonant intervals has now been found? No, it does not, as the fit with empirical phenomena is actually far from watertight. How, for instance, is it that the minor sixth, with vibrational pulses coinciding every 40th time, is still a consonance, but not the dissonant second, where the pulses coincide every 72nd time? Or, perhaps even more problematic, how is it that such harshly dissonant intervals as were customarily associated with the ratio 7 to 4 and 7 to 5 had their pulses coincide more frequently than with the minor sixth? To the extent that it was even tried to resolve such difficulties, Beekman went out of his way to meet them. Galileo did not. These attempted solutions were inevitably of an ad hoc nature. They were designed above all to save an account for which no ready alternative in conformity with suddenly current modes of thought presented itself. It is, however, characteristic of the physically realist transformation which the mathematics-imbued subject of musical consonance was meanwhile undergoing, that solutions were no longer sought in any deep meaning of constituent numbers, rather in certain real-world phenomena of sound, some of them freshly discovered. One somewhat later example is in work by Christian Huygens, who invoked the sixth and seventh harmonics, or upper partials, for shoring up his growing conviction that intervals with the number 7 in their ratios are pleasingly harmonious after all. So far these remained side issues. Not until the 18th century was a further knowledge of upper partials and other sounding properties of vibrational motion to be turned into the cornerstone of a mostly new, once again mathematical account of chord harmony, to which the names of the mathematician D'Alembert and the composer Rameau are customarily attached in the first place. Note, meanwhile, that amidst all this, the very idea of harmonious has fairly thoroughly changed its world-encompassing meaning. It was one major characteristic of the onset of modern science to give up any concern with all-encompassing questions like what it is that centrally binds the world together. Goethe's Faust, was die Welt im Innersten zusammenhält. With pioneers like Galileo and Beekman, the one, to be sure, an extraordinary genius, the other, in his own idiosyncratic way, an original talent, the entire occupation of those interested in natural phenomena has irredeemably shifted from natural philosophy to something perhaps best termed recognizably modern science. It is not just that numbers are not, after all, the right entity to capture cosmic harmony. On that point, they fully agree, that they see that the issue is not numerical and therefore mathematical and therefore abstract, but concretely tangible and therefore physical in the first place. It is surely true that the same numbers Zarlino had settled on do return in their respective accounts, but they do not return as numbers as such, but rather as numbers expressing certain fixed and to some extent empirically testable relationships between specific concrete phenomena, notably vibrational phenomena. It is true in addition that these phenomena are indeed specific. No jump from there to some all-encompassing conception can be allowed in what may henceforth count as science properly understood and properly practiced. And so it may well look as if already in the first few decades of the 17th century, some daring pioneers had condemned cosmic harmony to the death sentence that, as the century came to an end, was gradually becoming, as it were, Europe's common property. As you heard me quote John Dryden, by 1687 cosmic harmony was still an at least poetically well-usable concept. One generation later it no longer was. The process has fittingly been called the untuning of the sky. If by, say, the second decade of the 18th century you were attending some musical performance, you would have listened to it the way you have actually been listening to the Praetorius piece played before I began to address you. In other words, I'm pretty sure that you listened to the piece without sensing in addition that it really signified a reflection, an inevitably imperfect reflection, of cosmic harmony. To quite some extent, all this is surely true. Yes, historically, we can draw a straight line that runs from what we have watched Beekman and Galileo pioneer in the domain of consonance to successors like Mersenne and numerous others who, as it were, further solidified their death sentence and made it known and persuasive to broader and ever broader circles. And yet, this is not the whole story. Meanwhile, 406 years ago, in 1619, a work appeared of vast proportions, which its author entitled Harmonices Mundi Libri Quinque, 5 books on the harmony of the world. That author, by the name of Johannes Kepler, shared to the full the conviction, established and further developed in by and large the same years in quite different quarters by Beekman and by Galileo, that numbers are not at all suited to inform us about how to demarcate the consonant from the dissonant musical intervals. Salino had shown how working with numbers easily turns you into a juggler, more precisely a number juggler, prepared to imagine arbitrary rules or even to come up with subterfuges so as to make some a priori settled point fit in, at least on first sight, with your grand scheme of things. Indeed, so Kepler argued at about the same time that they had, numbers do not give you the right approach to a proper understanding of how harmony rules the universe. Indeed, the scenario is fundamentally unable to explain how it is that only the numbers 1 through 8 but not 7 produce the consonant intervals. What at a deeper level is needed, Kepler argued, is to find the geometric principle that underlies the harmony of the world. And that principle, so he found at the end of a deeply digging investigation of certain three-dimensional geometric figures, resides in the arcs that are cut off the circumference of a circumscribed circle by regular polygons, in ways confined by 3 well-specified rules. I shall not explain any further how all this worked, but just show you a modern rendition of the net outcome. To Kepler, in this principal respect a full-blooded Pythagorean, though assuredly a Christian one, the ratios that produce the consonances are much more than just that. They are nothing less than the logoi cosmopoietikoi, the world-building ratios that had served God while at work to create the world. Therefore, you do not find these ratios back in music alone. You equally encounter them, as Pythagoras had vaguely surmised, in various constitutive elements of planetary orbits. Take, for example, the planet Saturn. When farthest removed in its orbit from the Sun, its speed is 106 seconds of arc. When, about 15 years later, it is closest to the Sun, its speed is 135. This yields in a very close approximation, which Kepler carefully takes out. Sorry, yeah. The ratio of 108 to 135, which, when you perform the division, reduces to 4 to 5, the ratio of the major third. Similarly so with the orbits of the other planets. Here's the outcome in the next picture. And let me add just in passing that in making this pseudo-discovery, Kepler also discovered, as a kind of byproduct of his harmonic concerns, his immortal third law of planetary motion. If, by way now of a coda, we throw a look back at the entire period I have been addressing, we observe that the very conception of cosmic harmony, invented by Pythagoras and codified and established by Boethius, found itself profoundly challenged at two distinct occasions. The first challenge rested in how to overcome theoretically the introduction of thirds and sixths in chord harmony, doing so in ways that left the very conception of cosmic harmony intact, though no longer its traditional numbers. The man who eventually did just that was Joseph Zarlino with his scenario. The next challenge followed within a generation. Now the very effort was questioned to have numbers not only define the consonances, but also demarcate them from all other dissonant chords. Such critical questioning took for its principal direction a much heightened awareness that musical sound is real, a physical phenomenon, and that sheer numbers are far too formal entities to fulfill that role. Thus Galileo and, along other lines, Beckmann began to explore a physical approach to vibrational phenomena, with outcomes that just ruled out any conception of cosmic harmony, or even of musical phenomena standing for anything more than just themselves. This physical approach quickly prevailed. Not that these early scientists and those who followed in their wake were the only ones to bring about the demise of cosmic harmony. Certain developments in music itself, likewise much on the rise during the 1610s, 1620s, contributed to its demise as well. One major case in point is the rapidly increasing autonomy of the musical instrument, notably, but not of course exclusively, of the keyboard instrument with its fixed tuning. Another is the rise of monody in the early Baroque style, and with it, increasing use being made of dissonant intervals like the dominant seventh chord. To this broad picture, there's one major exception. It is, of course, the case of Kepler. While wholeheartedly agreeing that numbers are both too abstract and too much liable to arbitrary abuse, and that they can serve at best as a pathway toward reality but cannot stand on their own feet, he neither wanted nor saw any need to give up the conception of cosmic harmony itself. To the contrary, he set up a major rescuing operation. In retrospect, inevitably, he did so in vain. The very foundations on which he built fell apart quite soon after his death in 1630. Nonetheless, when we oversee the entire development I have been sketching, we find in the history of the rise, and in particular the fall of cosmic harmony, a great deal of needed criticism, often leading to constructive outcomes, but only two, as it were, ultra-constructive efforts to put cosmic harmony itself on a new footing. The two men who made these efforts were very well aware of the full value of what they sought to rescue. The one who made the heroic attempt was Zarlino, the other was Kepler. The works in which they did so, the Istitutioni Harmonicae in hardly lesser measure than Harmonica Mundi, stand as perennial monuments, meanwhile almost wholly obsolete, yet still very much worth reading or at least perusing. They testify to a most impressive intellectual construction. Cosmic harmony was, perhaps unfortunately, yet inevitably so, doomed to decline, then to demise, and finally to oblivion. An oblivion that, thanks in good part to several like-minded historians of my acquaintance, but also thanks to your kind attention over the past 3/4 of an hour, is still being alternated with brief moments of remembrance and efforts at historical understanding. Thank you.
All right. Professor Cohen, thank you so much for an absolutely fascinating and I would say much needed, at least for me, explanation of such a complex historical process in which I think we all face this or that term, but I think at least for me it was the first time it was thoroughly explained and it made sense. So thank you so much for that. So let's start with our question session. Does anyone have any comment or question or critique for Professor Cohen? Maybe yes. So Stephen, go ahead.
I think I'm on,
Yes.
and I just want to mention at the outset, Professor Cohen, I read your book, Quantifying Music, maybe 30 years ago, and it's been a
Oh,
cornerstone of my teaching at the University of Cincinnati, where I have been teaching courses in the history of music theory. We get to 17th century, we go carefully through this history, and it's always fascinating. And so hearing you talk, just I recovered the initial excitement that I felt when I read your book. I'd just like to ask, I just learned about this event very just last night. So I didn't have quite enough time to prepare. But there are a couple of things I that come to mind. One is where you would place Joseph Savour in this. Could he have come earlier? Could somebody with those kind of questions and ability come a little earlier in the picture and it might have changed things? And the other question is about music itself. When you're playing an instrument, you feel the vibration of the instrument. It's a kind of very physical thing. And it seems that the cosmic harmonists who are dealing with number are almost divorced from that sensation of vibration that you feel from a string, from the instrument, in the air, and really through your body.
Um, okay, first question about Joseph Sauveur. I'm actually, I know I've never studied him in any detail, but he is late 17th, early 18th century. And what distinguishes him from others is that for him, um, the analysis of sound stands almost on its own for certainly for predecessors, also for most of his contemporaries. Sound comes as well, the material of music, so to say. Sauveur shows little interest, at least not in his writings, in music at all. Sound is for him a phenomenon in itself that he wants to understand more about. That's of course vibrational issues and harmonics and so on and so forth. And I think he's the first where music is hardly part of what he's doing. The second, I think, yeah, given that when you listen to music, the vibrations go, so to say, through your own body and certainly through your head when you're listening. How is it that for so long theorists confined themselves to abstract numbers and well, noted, of course, that the numbers stem from vibrations, but didn't move on to examine vibrations as such. Is that what your question comes down to, more or less?
Yeah, yes, that's essentially it. Yeah.
Yeah, yeah. Okay, that's not an easy question to answer. And it is, I'm inclined. Okay, it is one portion of the whole question how modern science could come into the world in the first place, which actually is a
Yes.
subject I dedicated a later book to. There are all kinds of things that stem from antiquity where we would be inclined to think, now please keep on thinking, why don't you see that? But apparently there is so different a frame of mind that it doesn't happen without we having to think, well, they were a bit stupid or whatever. It's the whole idea of an empirical science where you take phenomena, natural phenomena, well, as it were, as such, and try to analyze them. That happened, that hardly happened. What the ancient Greeks did was, well, natural philosophy, which means that you create a system from a very small number of principles taken to be absolutely certain. Like Aristotle did, and like the atomists did in a different way. And I mean, when you see Beekman, he starts with atomism, but he doesn't leave it at. He gets an interest in how these atoms, he calls them globules, but basically the same thing, how they move, and he comes up with certain rules for their motion. In retrospect, you say, come on, Democritus wasn't stupid. He could have thought that as well, but it's really different frame of mind. Now, of course,
Yes, thank
I
you.
realize that this is only another repeating the question as if it is an answer, but well, I think
Yeah, I appreciate hearing your thoughts about it very much. It's very helpful. And I just want to mention one thing that some years ago at a conference, the music theorist David Huron was, in a sense, talking about your book and your work, and he felt that unfortunately the scientists of that time chose an unproductive question. He felt the question of ascertaining what's consonant about consonants and dissonant about dissonance, that just was not a great question, and not something that lent itself to a successful and progressive
yeah. Well,
conclusion.
that's one of the great things of Pythagoras, of course, if
Yeah.
you live, but at least the Pythagorean school, which certainly existed, to realize that yes, there is a basic distinction there, and that it is connected to something else.
Yeah.
I mean, how can you make music if you would use consonant and different all intervals indiscriminately? You don't get very far.
Right. Exactly. Yeah. Very much. Thank you. Thank you so much. Pleasure to talk to you and to meet you this way. Thank you.
Any other questions? If not, maybe I'll jump ahead and ask one because Professor Cohen, you mentioned briefly the experience of listening to music and how it itself changed in light of these changes that you outlined. Can you talk a bit more about this? Because I sense that, or actually maybe I should ask that. Is it not deeply dependent or experiencing, let's say, music as is representing the cosmic harmony? Isn't it depending in education, in people that were educated and learned about the cosmic harmony and all of its implications? Can you talk a bit more about that?
Actually, I know very little about that. I have examined this kind of thinking in terms of cosmic harmony, and how it came to an end. What I said at the beginning, we must assume, I mean, that people were listening. I mean, let me, there's another way. You know that there's been a time when I very much played the church organ with a definite preference for music. For the organ, I tend to regard Mozart as a dangerous innovator and hardly any pleasure. But
Don't we all? Don't we
I
all?
came to the realization that the organ, there are two, very roughly speaking, there are two periods for the organ. From very roughly early 19th century or so, it turns into an imitation symphony orchestra. Before that, it is the closest you can get in a musical instrument to the harmony of the spheres. The organ, the church organ, is the embodiment of cosmic harmony. So it's a fundamentally different instrument, and I mean that's not just my imagination, although of course it's a nice way to make an impression with my own preferences, but it is definitely the case that that's how the church organ was regarded in earlier times. That's part of the reason why so much effort was made. It is one of the most intricate technological achievements of the pre-industrial period to build these church organs. As I wrote, I learned to play the organ on an 1634 organ in Leiden St. Peter's Church with 3 manuals and of course one pedal. Wonderful instrument. You feel it while you are playing, and it is such a different experience from playing Bach or playing Zeta Frank, for instance. It's a different world. Okay. And okay, why not give you also an answer even a bit more personal? I've often wondered the music I love most. I'm not religious in any way, but why is it that Monteverdi's St. Mary's Vespers strikes me more than anything else? I have to keep quiet even or I will burst into tears. I'm not religious. St. Mary, I don't care about her, so to say, but in my own way, it has so much more to say than the music and Monteverdi's greatness that you also hear in his madrigals and his operas and you name it. There is a bit of an extra that, I would like to call it my personal cosmic harmony that comes to the fore in that particular Vespers, for instance. Well, this is maybe a different kind of answer than you expected, than I expected to give. But when it comes to, imagining what it must have felt like in those times and why the concept of a cosmic harmony, well, it has it's survived centuries. What made so many people feel at ease with it, live with it? Something like that.
That's a perfect answer for me. Thank you. Anyone else would like to make a comment, ask a question? Right. So if not, because I think it's this lecture. First of all, it was recorded, so we can watch it again. I definitely will watch it again and again to whenever I feel that this or that term is not absolutely clear for me. I really return to it because it was absolutely revealing, and I would like to encourage everybody else to do the same because that was really something. So I think we can get this session into a close.
Thank you for your
I
patience in
want
listening
to,
to me.
I want to thank Professor Cohen for a wonderful lecture and for being a great sport in organizing it and in scheduling it. And it's been a pleasure both to listen to you and to correspond with you. And you'll probably hear from me some more with some more questions that I don't want to
Do my best to
give
answer
away.
them. Yes. Okay.
Thank you
Goodbye.
so much.
Yeah.
And
Goodbye.
I wish everybody a good evening and see you soon. Bye bye.